So do you think my writing's getting better over the years, over the months? Isn't that fantastic? So, all right. I'll stand close to the microphone. I think we do have people online, and we will record this. And so I presume we'll take this the same way as we did last time. What I'll try and do first is give you a set of equations, which should be the full set of equations that you would need, so long as you know how to understand them. And of course, you realize from looking at past exams and maybe experiencing the last exam that you do need to understand what's going on. So to reiterate from the email I sent very early this morning, 3 questions, 110%, passing grades, well, full score is 100%, so you get a 10% boost, which is fine. Nominally 90 minutes, but you can stay as long as you wish. We'll start out at 8 o'clock in the 3 locations that were mentioned in the email. One was Hostler, one was Chambers, which is right next door to here, and one was Life Sciences. So if you don't understand the abbreviated names, I think it's Chambers, Life Sciences, and Hostler. Hostler's, of course, Hostler 26 is the room which is in Dyke, but actually you enter into it from Dyke, but physically it's in Hostler. 3 questions. It covers Bernoulli, conservation of mass, conservation of momentum, linear rotational. There is a Bernoulli question on its own, something related to stuff you've seen. There are 2 other questions which are a mix of conservation of mass and mainly conservation of momentum. And so we'll talk about those concepts today. The equation list that I'll give is, I think, a set that completely includes everything you need, as long as you know how to use it. And so I'll maybe spend some time doing that. So maybe today I'll entertain questions about what's on the test. Then we'll go back to talking about the concepts that we need that you need to have a command of, and then we can also go through the 20 or so pages of this cut down review that we have as well, just to reinforce ideas. Not to go into any great detail, but to maybe bring out the major points. Okay, so that's the plan. Anyone have a different plan, better plan, worse plan? Any questions about the test? Bring your own equation sheet. There will not be one provided. It can be whatever you like to bring on it. And it's up to you to fill up that sheet as you so wish. Okay. All right. So I started writing down what I think are the important relations. So there are three topics. So the first is Bernoulli. You should well know by now the Bernoulli equation. It doesn't matter whether you write it from upstream to downstream in the stuff that we'll do here, because we don't have pumps or losses in the system, but typically just out of convention for what we'll do later, we'll do upstream and downstream. Remember that these are all in the same units. I like it write it this way. You might like to write Bernoulli in a different way. This is the absolute way of writing it, not the differential form. Pressure head, elevation head, velocity head at the upstream location, and the complementary variables downstream. The velocity that we measure is a streamline velocity, so it's in the direction of flow. It's kind of important. It's not a vector, it's just a single scalar magnitude which is aligned along the streamline. Streamlines define the locus of flow that nothing would cross, and so two parallel streamlines, or for that matter kind of three parallel streamlines, or three adjacent streamlines because they're not quite parallel, define a flow tube. A flow tube has a cross-sectional area going in, a cross-sectional going out, and our statement actually for conservation of mass in its most simplest form is this, which is often adequate for the things you need. Bernoulli expression, if you want to solve it, you need to know everything but one variable. If you know everything but two variables, you have to constrain it in some other way, and typically you'll use conservation of mass to do that. So that's the simplest statement of conservation of mass. The other statements of conservation of mass have come from Reynolds transport theorem, which we won't go in today, but relate to, I'll write it out in just longhand, density times a rate of change of volume with time plus a volume times rate of change of density with time plus mass flow rates. Sometimes we write this as the sum of mass flow rates has to equal 0. This term here is the accumulation term, which is a rate of change of the product of density and volume. So this is just the separation of that, and differentiation by parts. Increase in the sign convention, increase in density, increase in volume, and mass rate out are all positive. And so that's worth knowing that. So in doing the accounting, we need to do that. And we've used that before. What else can we do? Do we need to do anything else? Yeah, I guess the other thing that we also know is the fireboat example, which we've used on multiple occasions. And that is that the velocity of fluid coming out of this versus the velocity of the control surface or volume together has to equal the velocity to a static observer. And I guess always for us, this sum of mass, if we write it out in longhand, so sum of mass flow rate is equal to what? a density, an area, and a velocity. The velocity is the velocity of the fluid relative to the control volume. So in other words, if you think about the fire hose coming out of here, it's the velocity that comes across this control surface. And so that's probably an important thing to recall. Right? So that's Bernoulli, conservation of mass. And so those are the two expressions that we deal with for that. And the final set of expressions are for conservation of momentum. And that falls in two categories, I guess. See, the easiest way to write this, yeah. Two expressions. So directly from this, velocity of the fluid out of the system plus the velocity of the control surface multiplied by the mass flow rate the sum of these equals sum of forces. So remember that this is a scalar magnitude, right? These are all scalar values, have magnitude and sign, so plus or minus for out or in, but have no direction. These are vectors, and typically we've not really worried too much about that, but this would be for resolving, say, in the x direction, and this would also be for flow velocities in the x direction, importantly. Mass flow rate is just out or in, just as before, so it doesn't have direction, but this component here is would be the velocity in the x direction. So in other words, static, if you like, in the same way as this. If you want to get the power out of this, the power is just equal to the static velocity times the force. So force times displacement over time. Force times displacement is Newton meters. Newton meters per second is power, which of course is named after Mr. Watt, George Watt. And so this is linear. If we look at rotational momentum, then it's very similar. It's the sum of a radius cross product of W plus VCS, a mass flow rate is equal to the sum of force, let's do it the other way, a radius cross product with the force. And so this is what we've called before the torque, T. Same as before, mass flow rates. In terms of a diagram, if you see fluid popping out of here relative to this arc, then this is the radius. This is V theta, which is what we want. So this is in the, bless you, this is V theta static, if you like. So it has to be resolved in that way. What else? This would be, I suppose this would be the force that we'd have to apply. Let me at least be, oops, let's at least be true to the sign convention. This is the force, and of course the torque would just be the force times the radius. Remember the right-hand rule, thumb. Look, I'm looking down on it, so positive is the direction you see on the board. And I think from the power from this, we've used a different term, but it is the power nonetheless. It's just the torque multiplied by the rotation velocity in radians per second. So torque, which is a force times a length, multiplied by radians per second, is just force times length per second, which is the same as the rate of doing work, is watts. So that one sheet will get you through, so long as you understand how to be able to use those. I'm pretty sure you don't need anything more than that in terms of other things that you'd know. Okay? So I'm happy to go through, and I plan to go through some material that will kind of exercise those, but that's basically the material that you should, really covers everything that we've talked about in the last, I guess, probably 4 weeks worth of work, right? 2 weeks for Bernoulli, 1 week for conservation of mass, and 1 week for conservation of momentum. Okay. Any questions before we go? Yeah.
No Reynolds transport.
You don't have to derive anything like that. No, that's for me. That's background of why this stuff makes sense. It might not make sense now, seeing it for the first time, but if you see it in the future, then it'll make sense. Yeah. So that's the reason for introducing these things in this nice package, Reynolds transport theorem. Okay. So you have that. This should all be recorded, so it should be there, right? So if there aren't any other questions, we can come to that back. So today I'll go through this. I'll stay as long as people wish to be able to answer questions. Okay. So you see many of these things here, things that we've already talked about already. This is Bernoulli along a streamline. This is normal to a streamline. This is conservation of mass. This might be useful to pack away, I would think. Talked about material derivatives and streamline acceleration, trying to understand that. In the stuff we've just introduced, we've talked about this. These are bold because they're vectors, Vx, Vy, and Vz, but typically we deal with one component at a time. We can frame conservation of mass and conservation of linear momentum both in terms of Reynolds transport theorem, but ultimately when push comes to shove, the expressions that we deal with have been somewhat simpler than this. This is for transport, so I guess this one here was rate of change of density with volume plus density times rate of change of volume plus mass flow rates equals 0, as you know. This one is relative velocities, velocity of the control surface, mass flow rates equal sum of forces. They're vectors really, but you can deal with them one at a time. We have to adhere to the sign convention. I didn't mention the sign convention before, but you know this is positive out. This is positive in the positive x direction. And you know that these are also each positive in the positive x direction. So these are aligned with coordinate directions. This is out or in. This is coordinate directions. So mass flow rates are always aligned positive out of the control volume, negative in because of the dot product. This product here, as you'll recall. And these are always aligned positive in the X, Y, or Z directions, whichever you choose. So that's important. Likewise, for this, we've written this slightly differently. We wrote this as, and do think of it in this term. I'm just repeating what we've already written. Relative to the control volume, rate out, the velocity of the control surface times mass flow rate equals radius times force. In other words, torque. And again, it applies that this is positive in the positive coordinate direction. Positive coordinate direction, this is Z, the rotational axis. So positive is in, it doesn't really matter so long as you just realize that one direction is positive. That's all that matters. So in this case, it's positive counterclockwise, as good as anything. And those have to be done consistently. This is positive out. And of course, m dot is just the product of the density times the area across which it flows and the dot product of velocity, right? So this is what gives it its positive out, negative in component. And I guess this is what we just introduced before, which we called power equals shaft torque multiplied by rotation rate. So the units of this are always radians per second. And V is equal to 2 pi radians per second. So that's not right, is it? V is equal to radius times omega. This is the rotational velocity. So radius multiplied by the rotation speed, and this is in 2 pi radians. Second. Okay. And so those are worth 9. All right, so that's just really a repeat of what we've already said, maybe with a bit of elaboration. So, here's so in terms of big concepts, we made a big deal about manometer equations, and we've done some examples with those. Of course, you realize that manometer equations are actually just Bernoulli's equation with the velocity terms dropped out. So you remember that if you take Bernoulli, you probably don't need to make this into a class, do I? But so we've been adding these layers of complication, I guess, to what we do. But if the velocities are 0, as they would be in a static fluid, then we lose both of these terms. And then we can look at the differences in pressures as you go up and down. And so those differences in pressures as you go up and down just become the manometer rules. Z1 minus 2 is just a change in height. And if you want to get, so in other words, this expression goes to be Z1 minus Z2 is equal to P2 minus P1 over unit weight. And so if we just multiply this by unit weight, then this is no different. This is delta P. The change in pressure you get as a change in elevation multiplied by a unit weight. And so that's just the manometer rules. So perhaps it's interesting to think that obviously Bernoulli gives you that. If you go up in a fluid, then you change pressure by whatever the height changes multiplied by the unit weight. If you go up, you subtract the pressure. If you go down, you add the pressure. Likewise, if we do this in a fluid, as you go across a fluid, as you move horizontally in a fluid, you end up, any horizontal simply connected pathway gives you the same pressure at this point as it is here. As you go down this amount here, you add an amount of pressure equal to H1 unit weight of this fluid. As you go across here to this point, you're at the same pressure, and so you can just work your way through the system. And so you remember that the easiest way to do this, I think, is to take it as PA plus H1 gamma 1 gives you this point here, gets you here, minus H2 gamma 2 equals P4. And so if you know one of these, you can always anchor the other ones. And so that is typically, you've done that enough times that you probably know how to do that. So manometer equations, if you go down in a fluid, pressures go up, add pressures. If you go up in a fluid, pressures go down. If you go up in a gas, probably the density of the liquid is very small. The density of the fluid is very small compared to that of a liquid, and therefore you don't care. If it's evacuated, it's the vapor pressure, and so those are all worth knowing. Okay, but they do come out of Bernoulli, even though you perhaps don't think of them that way. I didn't mention Bernoulli's equation normal to a streamline. You can take what you want out of that. If you want to get pressures, we know that depending on where you are, because of centripetal force, as you go around a curve, if you're going to go into a dip, then you're physically compressed, as you can imagine, as you go into a hill and then trying to come out, just like you feel yourself sitting more rigidly in your seat in the car. If you go over a bump, you feel a reduction in gravity as you get thrown out of your seat. It's the same for fluids as you go around bends as well. And that is given by Bernoulli's equation, written in terms of 2 points on a streamline. The idea is that you can write the behavior at 2 points not on a single streamline. I guess it doesn't really matter which direction we're flowing here. But rather than flowing along this streamline, if you go across this streamline, then you can write the behavior at the outer radius, and you can write this equation at the inner radius. In this particular case, I guess we would know that P4 is atmospheric if it's on the free surface. So we'd, for instance, know this. And we can rearrange terms. So the fact that we have this slightly complicated looking integral here, which is evaluated from the origin to 0.4, so that's what this range of this integral is. And we have this integral here, which is evaluated from the origin to 0.3, means that if you subtract one from the other, you're really just evaluating the integral between these two limits, which is, I guess, this point here. And if you do that, then we end up with an expression here which allows us to calculate maybe the pressure at 0.3, which we'd like to know. If this is the free surface, this is atmospheric. If we know the average velocity along the streamlines, so in other words, we're assuming, of course, there is no velocity in this direction here because it's normal to the flow. This is the flow direction, this is zero velocity, and so it has to be this velocity. We're looking at the streamline velocity, and we're assuming that the velocities on both of these streamlines is roughly the same, and so we can take the average. If we do that, then we can calculate this component here. I guess the other thing that I didn't mention is that this integral is in the direction n, which is always pointing into the center of the radius. And so in this particular case, positive z is upwards. And so a change in z is equal to minus a change in n, and hence this term here becomes this term here, and becomes this term here. And this negative sign is a result of that. And so from this, we have some difference in these heights, which we can measure, right? The difference in Z4 and Z3, depending on which one we're subtracting from each other, would either be this length or the negative of this length, whichever we're using. We'd like to, whoops. Don't know why that comes and never goes, it does. So this might be the term that we're interested in getting. If we know the elevation of those 2 points relative to this axis, so Z4 will be larger than Z3 because it's above it. We have an average velocity. We have an average radius of curvature of this thing. And the integral, if we take this as being just constant, the integral between these is just the length between these multiplied by this. So in other words, this integral here evaluated over this. So the integral, I don't know why I'm doing this in so much detail, by the way, but never mind. It's just going to be equal to Z2 minus Z1. Sorry, not Z2. It's just this length. This is the length. So this is all this integral is. And so you multiply by this. So you have this term, you know what the elevations are, you know what the unit weights are, and the only other term you have is pressure. Okay. Yes?
On the exam, are you going to specify whether you want normal or along, like as far as the streamline you want?
Yeah, there's usually a picture, and it'll be clear from the example. So, yeah.
How do you know b squared over r is constant?
We assume.
Another one, since like ln, you end up like integrating it to ln.
Yeah, too complicated. Constant's good.
Okay.
We spent too much time on this anyway. Yeah. So you understand what that means, of course. Yeah. It's always good to get me after my first pale ale of the evening, so always in better humor. All right, so yeah, so along the streamline. So we have Bernoulli's in two orthogonal directions. We've just gone through the one with curvature. You've played around with these examples. Is that right? So did you do some examples where you had to take the variation across? You're given a distribution.
It ended up being like you would integrate it with changing r.
Yeah.
And it would end up having to be like ln.
Yeah, fine. So, yeah, assume it's constant, but maybe you don't have to do that either. So,
Thank you.
welcome. My pleasure. All right. What else? So Bernoulli's we know. Be clear about when you talk about conditions. When you're in the flow of the stream, that you'd have a velocity, and when you'd be at a point where clearly there's no flow in this pipe, it has to be stagnant. So if you go into the neck of this pipe, clearly the velocity out here has to be finite and perhaps unchanged from the upstream velocity, but somewhere in this pipe the velocity has to be zero. And so this is kind of the component that looks at whatever the pressure is that you develop in this pipe. And of course, actually, if you're in class today, you realize that the pressure that you get in these is actually just like our Euler number. You kill the velocity and you generate a pressure as a result of it. So not really relevant to what we're doing tonight, but that's kind of where that stuff comes from. We talked about free jets. Stop me, by the way, if you want to talk about other things. Talk about free jets. We've talked about, the code. Large means that V1 equals 0. If V1 equals 0, it makes life easy because all of a sudden you lose this term. If you lose this term, then all of a sudden the velocity you have coming out of this orifice, irrespective of how large the orifice is actually, which is kind of interesting, is just the same as this number here. Square root 2g over h. And actually, it's kind of an interesting expression. I say that it doesn't matter what this orifice is. It's actually exactly the same velocity as if you drop this pen. It's just free fall by gravity. And it happens that it's driving flow in this particular case, but that's physically what it means. So here the pressure is 0 because it's atmospheric. Here the pressure is 0 because if you go out to this point, the pressure has to be 0. The pressure is acting horizontally has to be 0. And because we know that pressure acting at a point is always 0, then if the pressure acting in this direction is 0, then by definition this pressure in this direction has to be 0. That's the rationale for that. So the pressure here is 0. Pressure here is 0. Velocity is 0 because it's large. Velocity here is not 0. And the difference between these elevations is just z1 minus z2. And if you use that, you end up with the equation for a free jet. I think we also went through the case where if you take this point here, you'll find that the velocity of the free jet is no longer just lowercase h, but lowercase h plus uppercase h. So it really is just free fall, nothing more than that. And that's why it doesn't care whether the orifice is a needle or whether it's the size of my head. It'll still come out as the, or your head, the same comes out at the same velocity out of the system. And we spent some time doing that. All right. Doesn't matter if it's coming out horizontally. It's the streamline velocity we get. And so if this tank develops a hole in its side, or develops a hole in its side at this particular location here, the velocity it comes out of here is the streamline velocity, and it's a horizontal velocity of whatever that is. And so it's really just driven by gravity. You see that the unit weight or density doesn't even play. So if it's mercury falling out of here versus water versus gasoline, which is less dense than water, it's still just falling at the same velocity as a pen in a vacuum would be. No air resistance and just free fall. No frictional losses. Okay? Everyone okay? All right. I don't know how many of these we've got to go through. Again, what are the key parts of this? Flow comes out of a tank. It's a static tank. Does it say a large tank? Yeah, of course it says a large tank. We know what that means. It means that V1 is 0. We know that P1 is 0. You know that the elevation is the elevation of Z1. And you can write an expression to get the streamline velocity out of here, which would be V2. It's coming out into the atmosphere, so the pressure at that point has to be equal to 0 for the same reasons that we said before. It's acting from the side as 0, outside the jet, and so since pressure is acting in all directions have to be the same, then it's also pressure 0, and I guess the elevation of this would be Z2. So what is the key point in this? To calculate how high it goes. You know a streamline velocity here. You know that the horizontal velocity at this location has to be exactly the same as the horizontal velocity here. Not the streamline velocity, but the horizontal velocity. And so V2 cosine theta is the horizontal velocity. Because anything moving that isn't acted on by some force, the only force would be wind drag, which we're not considering, keeps on going, Newton's laws. And so the velocity at this point in the streamline has to be exactly the same. And so V3 has to be exactly the same as this magnitude. We know this. We know the angle it comes out at, so presumably we can calculate what V3 is. So that allows us to be able to do something. If we can calculate V3, then presumably we could write Bernoulli's equation that has this velocity V3 squared over 2g plus the pressure plus the elevation, which we don't know. So we know this is 0, we don't know this, and this has to be equal to v2 squared over 2g plus p2 over unit weight plus z2. We know this is 0, and we know this is a 2. We know this as well. And so we have everything we have to calculate elevation. If you know elevation, maybe you can calculate how long it stays in the air. If you know how long it stays in the air, the time taken to get from this point to this point, throwing it up until it arcs at 0 at the top of the arc and drops down, is exactly the same as if you take it up to the top of the arc and you allow it to drop down through point Z2. And so if you know the equation for that, then you can say something about calculating how long it would take to do that. If you know how long it takes to do that, and you know the velocity it's traveling at horizontally, you can calculate how far it would go in the time it takes to reach its apex. So that's it. Comes out of the jet, has a velocity. You know the horizontal velocity comes out of the jet. The streamline velocity at the top of the arc has to be the same as that horizontal velocity, so you can figure out what the height of the arc is. So, yeah, the height of the arc is from Z3. If you know the height Z3 at the top of the arc, you can drop it and calculate how long it takes to hit the deck. If you know how long it takes to hit the deck, and you know how fast it's traveling horizontally, you can calculate how long it takes to get to the top of its arc, how long it takes to come down to the same height on the other side, this height. And if you wanted to, down here as well. Okay. And you've seen that in the previous question. So, okay. So that's the kind of thought process. Nothing will be as complicated as this in terms of, it's made complicated in this particular case because it's got this length that comes out of here, makes it tough. You've seen another one in another exam that does that, so might be worthwhile checking out. Conservation of mass, well, we certainly know much more about that than we did when we talked about this particular slide. We really talk about conservation of mass, so it's not just area times velocity, but it's area times velocity times the density. Typically the densities in and out are the same, and so we don't worry about it, and then it becomes conservation of volume, but it is really the simplest statement of our conservation of mass equation. So I think you guys know how to do, guys and gals know how to do that. We did this one in class, kind of a bit involved, a bit too esoteric. I'd be happy to go through it if you want, but yeah, it's not. Manometer equations. What are the main points here? The main points, I suppose, are to realize how to write the expressions. You can write certainly Bernoulli between these 2 points here. And you just have to get used to figuring out what the conditions are. If you look at the velocities, the elevations, and the pressures, then we know that this is not equal to 0. This would be the true velocity. And of course, velocity 2 times A2 would equal to the flow rate, which I think is really what you're after in this case, I'm guessing. Yeah, what's the flow rate? Q. And so we need to figure out what V2 is, and we don't know what it is. We just know it's not 0. We know an elevation. And I presume we know a pressure. We know a pressure because we can migrate this point here up through the manometer tube to be able to at least get a differential pressure between P1 and P2. We can write the behavior at this other place. Velocity 1, pressure 1, elevation 1. Elevation 1, if we take a datum through here actually, the Z1 and Z2 will cancel out. We actually know them, but they just cancel out. The pressure we don't know. But we do know that the velocity has to be equal to 0 because we're taking 0.1 inside this tube. And so presumably we can write Bernoulli's equation in terms of the terms that we have remaining, which are P1 over unit weight. We don't have this. Is equal, I'll leave a little space there, is equal to P2 over unit weight plus V2 squared over 2G. And so I say that because the elevation terms have gone out because we're at the same elevation. One velocity term is there because it's not equal to 0. Okay. And this pressure we don't know. And so the easiest thing to do is just subtract off from both sides P2 over unit weight. And now we're left with something which is just a differential pressure between 2 points divided by unit weight of the flowing fluid. And so hopefully what we can do is we can do our manometer equation to be able to work our way from this point all the way through here to calculate what the pressure is at this point, which will be different. And we can use that for delta P. So we use the manometer equation here to get delta P. It will be as a function of the gauge fluid. Actually, delta P is just going to be equal to just this height minus the, is what it will turn out to be. So delta P is equal to the height differential multiplied by the unit weight of the gauge fluid, not the fluid in the pipe. This is the pipe fluid. And so be aware of that. Okay? So that's kind of a typical, and you've seen those, I think there was a nozzle squirting some direction with these things in the past. And so that's maybe worthwhile having a look at as well. All right? Yep, go ahead. 2 questions. One at the back first. Furthest back.
There was an example online where we were solving for H. And what does it mean if H comes out to be negative?
It means the way that the figure is drawn is backwards. So I know that, yeah, it was this nozzle one. So if H came out to be negative in this case, then it means that instead of the manometer looking like this, it would actually look like this. This one would be higher. Just means that the pressure differential is in the opposite direction. Okay. Yes?
I just don't understand why P3 plus gamma L is equal to P4 plus gamma L. I don't think that's clear.
Say that again. How, what is what?
P3 plus gamma L equals P4 plus gamma L.
Where's a P3?
Right there where you have the Manometer Equation for fluid.
This one here?
Bottom of the page, yeah.
This one?
At the bottom.
Oh. This, oh, the stuff I haven't written that someone else has written?
Yeah.
Okay, get me there. This one?
Yeah.
How would I do this? I would do this as, I would write this as P1. What does this give us? P3. I would write this as P1 minus L gamma fluid gets us to this point, gets me to this point, gets me to this point. Minus H gamma gauge fluid gets me to this point, gets me to this point, plus H plus L unit weight of the fluid equals P4, P2. I would get this. So can you live with that? Okay, that's how I'd do it. Yeah, I'm not really sure exactly what's going on here. P1 is equal to P3. Is it the same equation? So in other words, in this, you could now rearrange this to being, what do we need? We need delta P is equal to P, so delta P is going to equal this magnitude here. So do I need to use this? I guess I could use this directly, as since I've written this expression here in terms of this. So we have P1 minus P2 is equal to unit weight times V2 squared over 2G. And since I now have that P2 minus P1 is equal to minus L gamma F minus H gamma G plus H plus L gamma F, and this is the component, just negative value here. You can substitute in here. So now you don't need to solve for this. We have values of L and H in each case. Do we need to know what this L is? I guess the L amount is the same in each case. The L should subtract from each other, right? So this term here and this term here subtract from each other, and we're just left with H times the unit weight of the gauge fluid. Is that right? So this is equal to H multiplied by gamma gauge. And so this is almost this, right? Not quite. The differences in the gauge fluids. Is that okay? Well, this looks right. All right. So, does that make it any clearer, or does that make it worse? So, yeah.
I don't really know how they got to P3 plus gamma L equals P4 plus gamma L.
P1. Okay. P1 equals. Well, okay, because it's. You start off here, so I guess you could write P3 plus L gamma fluid equals P1. That's it. I guess I could have answered your question a bit easier. That's it, right? All I'm doing is I'm starting off here, and I'm going to this point here. So the pressure here is P3. If I add to that pressure L times the unit weight of the fluid in the pipe, which is this term here, then I get the pressure at this point here. Likewise, all they're doing here, so they're also saying that P3, all they're doing here is also saying that P3 and P4 have to be the same pressure, because you can get from one to the other and you're still on the same level. Okay? So, all right. So anyway, but the bigger picture for this, write Bernoulli's equation in terms of the two pressures, upstream and downstream. Solve the manometer equation separately for the delta P term. And when you substitute them together, you should come out with one value for this term here. If you know what V squared is, then you have enough to be able to calculate what the flow rate is. So, are we losing people? Rate of change in time. We didn't deal with this in class, so that's off the counter. Control volumes. Fixed, non-deforming, moving, and deforming. We've talked about those. We talked a little bit, we've certainly talked about this expression and the sign convention we apply to this. We went through some examples that use that for different, just to show the concepts that whether you look at the same problem, whether it's a static control volume or a moving control volume or a moving and deforming control volume, for the same problem you should get the same result. I'm not sure that we really went through this. I'd be happy to go through this if people want me to. But I think we just reinforce the ideas that rates of mass flows going out are positive, mass flows in are negative, rates of increasing density are positive, rates of increasing in volume are positive if it gets larger. And really it is, this basically is rate of accumulation minus rate of depletion. Depletion and accumulation. Or depletion is net in, net out minus net in. And so we've used that a variety of times and in lots of different ways. Okay. What else? Well, so conservation of mass. We talked about the sign convention, which is, I guess, this. We've written it slightly differently, but it ends up being the same, which is rates of change of volume times density, rates of change of density times volume, mass flow rates equals 0. We have to be a little careful. I guess the only thing we need to know is that this mass rate of change is equal to a mass flow rate, so it's a density, it's times an area, and it's multiplied by this relative velocity. This relative velocity relative to the moving boat. And so V static is equal to relative flow rate, and it's relative to the control surface, right? Plus the velocity of the control surface. And so we've always used this kitschy view of things to represent exactly what's going on. And of course, the velocity that we see it at is this velocity of the static observer. And so you need to be able to make that substitution. It's not very difficult for mass flow rates because we know we always have to be using this relative velocity. And so that's perhaps not so challenging as others. When we deal with conservation of momentum, then we have to perhaps write this so that this term here is really, this is relatively important, right? To be able to include this. If it's static, then this term just drops out, and this is just the velocity relative to an observer. This is V static. And so it's important to be able to deal with this. So remember the sign convention, mass flow rates, we've used uppercase M, are always positive out. Velocities, which we've used for these, are always positive in the coordinate directions. And so maybe that's best reinforced with an idea, or an example rather. We went through this one in class. I'll let you look at it again. But if we're doing the accounting, so the mass flow rate term, is equal to density times area 2. So we know that this area times density, this is the normal to the boundary velocity. It's out of the system, and so by definition, this should be positive. So this is positive, but this is in the negative x direction, so this term is negative. So overall, this term is a negative times a positive, and therefore it should be a negative when you do the accounting. This term here. I'll make it smaller. All right, quite important, obviously. This term here, flowing into the control volume. So the dot product is negative because it's flowing in, not positive. So this here is negative. The flow velocity is in the positive x direction. And so this term is positive. Positive times a negative is still a negative. And so this term here has a minus sign attached to it, sign convention. The pressure acting on this face, if you cut it off, is in the positive x direction. Pressure times area is the force, and so this is positive. Acts here. The force, as we've drawn it, we've chosen to draw it this way. We could draw it any way we want. The force that we're applying to hold this in place is in the negative x direction, and so there's a negative sign that's here. And this P2 is atmospheric, so it's 0. And so you go through this and calculate what the magnitude of this force is, and if it comes out to be positive, if the magnitude is positive, then it means you have to hold it in the positive direction that you see that red arrow, which is pointing towards your left, which is, you can imagine. It should come out to be positive, I'm guessing. Not calculated, but or it isn't. No. It has to be positive, right? Because all of these other terms are positive. So the force is positive, and so the force you have to hold this in place with, as it's flowing water, I was going to use another term, flowing water out of this monitor, is to physically hold it with a positive F magnitude, which means it's a force in the negative x direction. Just by the way you define it. Yep.
Why is it plus PQ18? I don't even should that be negative?
Which one? PQ.
Is equal to P1A1 minus the force plus.
This down here?
Yeah.
So this one is positive because the pressure is acting on the outside of this control volume in this direction, and it's of magnitude P, and it has an area A, and it's in the positive x direction. Okay? No problem with that. And this is negative because we've defined this to be our force.
Okay, what about the next term? PQ82, why is it plus?
Oh, because it's also assuming that the pressure acting here is acting in this direction like this and is P2. And it acts over some area A2, but actually it's atmospheric, and so we don't care.
So if it's ever open to the atmosphere, so it's basically pushing against it in.
Well, it's assuming that there's some pressure that we could imagine here that's in this fluid. And if the fluid is outside the control volume, it has to be acting physically on this surface. And so it's acting no differently to the fluid pressure that's acting here, if it's positive. And so it's just the way that we've defined the control volume. So the control volume that we've defined is basically this. And so on this surface here, the pressure, whatever pressure we define, has to be acting in this direction. On this control surface here, the pressure has to be acting on the control volume. Has to be acting normal to the surface. And it's outside the control volume, so it's acting in the positive x direction. Right? Okay. It happens to be 0 on the top one, so it doesn't make a difference, right? But that's the reason for that convention. Okay. All right. Any other questions? I think in this case, I don't know if you have to use relative velocities. We talked about the fact that the velocities that we define have to be equal to so what did we say? That the velocity plus the velocity of the control surface times the mass flow rate has to equal the sum of the forces. Whoops, no. And this is a velocity term as well. So this is relative to the static. Always. And so it depends whether the thing is moving or not. So I guess if it's anchored, then by definition the velocity of the control surface equals 0 and F is not equal to 0. Because for it to be anchored, you have to apply force to keep it in place. If it's moving, then by definition the velocity of the control surface is not equal to 0 by definition. And the force may be equal to 0, or it could be equal to some prescribed amount. I'm not sure what they're doing here. Yeah, it could be some prescribed amount. It could be 0, it could be some prescribed amount. And so how you deal with these problems depends on this. And so we did an example in class, the gas, decapitated cylinder, to look at how this would affect behavior. And so if it was anchored, then by definition, this velocity of the control surface is equal to 0. This is equal to the flow rate out of the static cylinder. That's the same as the velocity that's applied to the mass flow rate. So this mass flow rate is equal to an area times a density times a relative to the control volume velocity. And so since these are defined when you decapitate it, you can calculate the force you have to apply. Yes? Sorry, I was looking at you. Okay.
One moving scenario is the velocity of the control surface is 0.
That's a good point. Did I say that? Is that? Yeah. Yeah. It's not. Yeah. So yeah. So I was just. So it clearly isn't. In the moving case, by definition, the control surface has to be moving. Maybe it's some prescribed velocity, or maybe some velocity that you like to calculate. If you know the magnitude of the force, then you should be able to calculate this velocity. Yeah. Okay. And so you remember when we talked about the gas cylinder, we did it in two ways. Anchored, by definition, the velocity of the control surface is 0. This is the velocity of the air coming out of it, which we can calculate independently in that particular case. We could calculate it by Bernoulli, right? By writing the pressures and the velocities at 2 points. We'd like to calculate what V2 is. If we know what pressure 1 is, and we know it's a big cylinder, so the velocity is equal to 0, then we should be able to calculate, if we know that the pressure here is atmospheric, then we should be able to calculate what this is. The reality is, of course, that what will turn out is that if it's anchored, then we develop the maximum force, because the velocity it's coming out of is defined absolutely by Bernoulli's equation. Doesn't matter what the size of the orifice is, it will always be the same velocity. And since we know that this is 0, we know this, we know this, we have everything we need to calculate what the force is that you have to hold it in place. We just need to take account of the sign convention. If it is free to move, then it's the converse. If it's free to move, all of this still applies, right? This is just calculating Bernoulli's equation relative to this thing that's been decapitated. An unfortunate term in this day and age, unfortunately. And the velocity that comes out we can calculate absolutely and uniquely. And so now, if we know that maybe the force has to be 0 if it's static, if it's being held with some force, then what am I trying to say here? The other one was anchored, and therefore we could calculate the force that was applied. That was the only part remaining. If it's allowed to move, and the force by definition is 0, for instance, the only way that the right side can equal 0 and the left side can also equal 0, independent of what this mass flow rate is, we don't care, is if these two are equivalent to each other. And so that physically says that stuff is shooting out of the end of the cylinder as fast as the cylinder is moving away from that stuff. So a static observer would just see this stuff coming out of the end of the cylinder, it would just be flopping to the ground. Cylinder would be zipping off here, static observer would be here. The cylinder would be moving off at exactly the same rate as this stuff was squirting out. And so physically a droplet of fluid that came out of it would come out of the end of the cylinder, it would drop down to the ground, and the cylinder would be moving away. In the next time increment, it would be coming out of here, it would just drop to the ground as well. So that's physically the system. You could imagine the case where the force is not equal to 0, but in which case you'd be able to calculate the magnitude. If you knew what the force was, you could calculate what the velocity of the cylinder was. That's the other intermediate case. And I guess we also talked about the fact that we could calculate the power that came out of this merely as the product of the static velocity multiplied by the force. So this static velocity, in this case, the velocity to a static observer relative to the force that's applied. So force is in newtons, static velocity is in meters per second, so power is in units of Newton meters per second. A Newton meter is work per unit time is power in watts. And so, yeah, go ahead. Yeah.
Hey, so if it's moving, what force are you talking about that wouldn't be equal to 0?
You could be holding it with a maximum force, so it's static. You could be holding it with no force, so it's going at maximum speed. You could be applying a load to it, which is not the maximum force, but is larger than 0, and it would be going at a velocity intermediate to that.
Okay. Thank you.
Good question. Okay, other questions? Yeah, go ahead.
Yeah, so like the velocity coming out of it, which is like W, and then the velocity of like the control system, do you just take like the scalars of both of those and add them, or if they're like in opposite directions, do you take the sign convention with it?
Have to take the sign. Typically, you'll resolve them in one direction, but you need to be aware of the signs. If they're acting in, I mean, you have to, right? Otherwise, the sum of if these are just two scalar velocities and you add them together, they're always going to be positive. And so if you want this to equal 0, the cylinder's moving off this way, the relative to the cylinder velocity out of the cylinder is this way. So they're opposite to each other. So you have to, okay? Any other questions? I'll cut you a break. No rotating. momentum. What you can do is you can buy me a drink sometime to show your real appreciation. But actually the cylindrical ones are the same. So things going around in this direction, the water is squirting out in the opposite direction. You have to take the vector sums. If they're aligned, then it's just a straight addition or subtraction, but they have to be aligned. And so anyway, so leave that. So I will be happy to stay here and answer questions as people need. Yeah, so that's fine. That's not a bad deal. 3 things. So this thing, summary at the end. Actually, I think one of the best things to use is, I think the main features of what we've talked about today are the stuff that's on this.